Okay, so I wanted to go over the answers to the reaction energy diagram worksheet. All right, so when we're looking at these diagrams, remember you always have the energy of the reactants on the left, you have the energy of the products on the right, and this shows the reaction that you would have, the energy that you would have as the reaction progresses. All right, so this would be like for one individual molecule that reacts, how much energy you would have as it goes through this process. Right. So the first question, which represents the potential energy of the products? The products are right here. So if we assume that there's zero energy at this right here, then this arrow right here would represent that amount. So that answer right there should be E. All right. So what's the potential energy of the activated complex? Remember, the activated complex would be at the top of the curve right here. Again, an analogy for this would be like if this is a domino standing on its end, this is a domino that has fallen over. The activated complex is kind of like the domino on its edge. You have to put a little bit of energy into that domino to get it to the point where it's on its edge before it would fall over. All right. So the energy of that activated complex would be from here to the baseline. So that would be C. All right. What's the potential energy of the reactants? That's going to be A. All right. Which letter indicates the activation energy? All right. The activation energy is the energy that you've got to put into the reactants to get the reaction to occur. So that would be the difference from here to the top. So that is represented by arrow B. All right. So which indicates the heat of the reaction. All right, so technically it should be what's the change in the heat of the reaction. All right, so what's the difference in the amount of energy from here to here? All right, that would be represented by F. All right, and one thing I want to point out is in going in the forward reaction, that would be heat that has to be put into the reaction. So the reaction would be absorbing that much heat. Okay, so is the reaction exothermic or endothermic? All right, so in this direction here, all right, the reaction, if the products have more energy than the reactants, the reaction will be absorbing energy. All right, so this would be an endothermic reaction. All right. So, which indicates the activation energy of the reverse reaction. All right. So the reverse reaction is if you're going in the right to left direction. All right. So the amount of energy that you have to put in to get it up over that hump would be D. All right. What's the heat of the reaction of the reverse reaction? Again, it's the difference between the reactants and the products. So that would be F. All right. So you'll notice that F is in two different answers here. The difference is in the forward reaction, that is heat that the reaction would be absorbing, whereas in the reverse reaction, that would be heat that the reaction is releasing. All right. So is the reverse reaction exo or endothermic? All right. So since heat is being released, another way of saying that is that the reaction of the products, the energy of the reactants are higher than the energy of the products. That would make this exothermic if you're going from the right to the left. All right, so on the bottom, all right, taking a look at this reaction energy diagram, I've gone ahead and put a couple numbers on here. So the top of the activated process complex would be 240. The energy of the products would be 160. The energy of the starting materials would be 80. All right. So what is the heat content of the reactants in the forward product process? So reactants would be here. So that would be 80. All right. Heat content of the products. All right. Here are the products. Their heat content would be 160. All right, heat content of the activated complex would be right here. That's 240. All right, activation energy. All right, so how much energy do we have to get from here up to get us up over the hill? All right, so the way that you'd figure that out is 240 minus 80, and that gives us 160. All right, what is the change in the enthalpy? All right, the delta H of the forward reaction. All right, so remember, the change is always later minus earlier. All right, so 160 minus 80. And one thing I want to point out, if you do this, the answer you would say is, normally you just say it's 80. But when you're talking about a change in enthalpy, you want to include a sign. All right, it would be listed as plus 80. And the reason for this plus is to stress the fact that this reaction here would be one where you're absorbing heat. All right, where the energy here is higher than the energy at the starting point. So when it looks like this with the products up high, that's going to be an endothermic reaction. All right, so the heat content of the reactants in the reverse product, that's another way of saying what are the products of the forward forward reaction, I should say. So that's going to be 160. The products of the reverse reaction, if we're going this way, these would be the products. That's going to be 80. All right, the heat content of the activated complex. The activated complex is the same whether you're going forwards or backwards. So that's going to be 240. All right, the activation energy of the reverse. So how much energy do we have to put into this to get it up over that hump? That would be solved by doing 240 minus 160, and that's going to give you 80. All right, and what is the change in the reaction? All right, so the difference between here and here is the same as the problem that we did before. The only difference is that, remember, we're going to do the end state, 80 minus the beginning state, which if we're going in the reverse direction. So if we're going in the reverse direction, this is the end, and this is the beginning. So 80 minus 160 will give us negative 80. All right. So, so in going in this direction, you would be, the reactants are losing heat. And again, the heat that the reactants are losing is what would be given off as heat in the reaction. All right. So even though the change in the enthalpy is minus 80, this would actually feel warm because you're feeling that heat that is being lost by the reactants. All right, and the reverse reaction is going to be exothermic. All right, and going this direction, that is exothermic. Okay, so when a chemical reaction occurs, what reasons may a collision fail to produce a chemical reaction? All right, so there's two reasons for this. One is going to be, so remember, there's two things that are necessary. First, they have to collide with each other with enough kinetic energy. Basically, it means they have to hit each other with enough speed. All right. The second requirement is that they have to have the right orientation. All right. So first of all, low kinetic energy. All right. Maybe the temperature of the reaction isn't high enough. That would mean that the particles aren't moving that fast, and so that when they do collide, they don't have enough speed for the reaction to occur. The other possibility would be that it doesn't have the right orientation. When the reactants collide, if they're not facing the right ways, then nothing can occur. All right. So if every time a reaction occurs, if every collision between reactants led to a reaction, what determines the rate at which the reaction occurs? All right. So the only thing that would be, if every collision led to a reaction, that would mean you have enough kinetic energy every time they collide, and they have the correct orientation every time they collide. The only thing that would affect the rate of the reaction is how often they hit each other. All right. Remember, this question doesn't say anything about the frequency of the collisions. So if you have low frequency of the collisions, It just would not happen that often. All right. So, what's the activation energy of a reaction? It's the minimum energy that has to be added for a reaction to proceed. And how is it related to the activation complex of the reaction? So it is the same as the activated complex energy, this right here, minus the energy of the reactants. Right? So what happens if a catalyst is used? That's going to lower the activation energy. All right, remember, the analogy is like if you heat up a reaction, you're speeding up the particles. That's like saying you're going to jump higher in order to get over the hurdle. All right, you're giving more energy, so that helps you get up over. That would help you get up over this hump right here. But how else could you get up from here to here instead of jumping higher to get over the hump? How about just lowering the hurdle? All right, and that is what that's what a catalyst does. It lowers that activation energy. All right. So name 4 things that will speed up or slow down. I actually listed 5. All right. First of all, temperature change. All right. Generally, if you heat things up, the reaction is going to go faster. Second thing, changing the concentration. If you're doing, if you have the same amount of materials in less in less space, all right, there's a higher likelihood that they will collide with each other. All right. So it's one way of thinking about it is like picture a V-shaped pool. All right, and you've got a lot of swimmers in there. What happens as you start to drain the pool? All right, well, as you start to drain that V-shaped pool, all those swimmers get crammed into less space, and so the likelihood of a collision becomes much greater as the concentration goes up. Right. Next thing is if there's a gas reagent that's in the reaction, you can change the pressure. The next thing is by changing the particle size. All right. One common way that you could do this is grind your particles so that they are very finely shaped. All right, or finely sized. Essentially, sawdust is going to burn faster than a log of wood because the particle size of the sawdust is so much smaller. The reason that speeds up the reaction is it increases the surface area of your reactant, and so there's more chances of a collision if you have more surface area of your reactants that are exposed to other chemicals. And the last one is going to be adding a catalyst. All right, and again, that speeds up a reaction by lowering the activation energy. All right, so let's draw this diagram. So let's take a look at our numbers here. First, let's draw a graph, and you have to choose a y-axis. I looked at these numbers here, and it's like, let's add enough numbers so that we have more than enough space to represent what we've got. That's why I made my axis go up to about 500. I should have written time or reaction progress here. So you want to start with the activation energy of the reactants at 350. So 350 would be about right here. So you want to start off with a line that's going to be about right here. All right. We want the products to be at 250. That's why those are at this level. And we want the activation energy to be 100 kilojoules per mole. So we want the top of this to be 100 units than what the reactants were. That's because you need to put in that much energy to get it up over the top. So the top of this hump right here should be level with 350. Right? So is this exothermic or endothermic? This would be an exothermic reaction because the products here are lower energy than the reactants. And what can we do to lower the activation energy? And hopefully you realize by now, add a catalyst. If we did that, the reaction progress, it would have the same starting point, but it would have a lower hump right here. It's like a little bit of a lower hurdle, but it would end at the same place. All right. So hope that helps, and that's it for now.